Folks, in this video, we're talking about percent composition. What? All right, so objectives. I want you to be able to define percent composition by mass and determine the percent composition by mass based on a chemical formula. What? I want you then to be able to explain the difference between empirical formulas and molecular formulas. And then lastly, I want you to be able to determine the empirical formula for a compound based on the percent composition by mass. Wow, that seems like a lot. It's not actually that much. Let's get going. So percent mass composition or percent composition by mass, sort of the same thing. That measures what percent of the mass of a compound comes from each of the different elements it's composed of. And so this is a useful for technique if you're trying to identify an unknown but pure substance, or if you're a cool scientist and you've made a new compound and you want to characterize it. It's a pretty sweet step in that whole process. Well, for an example, let's talk about my dude glucose, C6H12O6. Glucose has a very specific percent mass composition or percent composition by mass. And so that is 40% of the mass of glucose comes from carbon. Measly 6.7% comes from hydrogen, and 53.3% comes from oxygen. Now, this might strike you as peculiar because most of the atoms, or 50% of the atoms in glucose are hydrogen, but only 6.7% of the mass comes from hydrogen. And that's because hydrogen is a very light element, at least compared to carbon and oxygen. So every sample of glucose anywhere in the world will have this exact same composition by mass. So any sample is going to be 40% of the mass rather will be carbon. So if you had 100 grams of this glucose, well then 40% of that 100 would be carbon, or 40 grams. And 6.7% of that 100 grams, or 6.7 grams, would be hydrogen. And you guessed it, 53.3% of that mass would be oxygen. Neat stuff. Well, if you want to determine the percent mass composition from a formula, here's how we're going to do that. First thing we need is the molar mass, or the total mass of that compound. So if we've got this guy, I can come up with the molar mass. I can look at my periodic table and how many of each element are in it and determine the overall molar mass of the compound. Well, next step we need is actually kind of part of that first step. It's to multiply the number of atoms of each element by the atomic mass, which, yeah, we had to do to get that molar mass. So it's a good idea to write down your work. Let's just do that real quick. I got carbon. It weighs about 12.01 grams per mole. Since there's 4 carbons, I multiply that by 4. I get the molar mass of hydrogen, multiply that by 8, for there are 8 hydrogens. I get my molar mass of nitrogen, and I multiply that by 3, because there are 3 nitrogens. And I'm just going to leave the molar mass of oxygen the same, because there's only 1 oxygen. Nice. Well, what I'm going to do now is divide the mass of each element by that total molar mass. I'm going to divide the mass of each part by the mass of the whole gosh darn thing. And of course, if it's a percent, I need to multiply by 100. So I'll take my mass of the carbon and divide that by the total mass, multiply by 100, tells me, yo, if you got this compound, 42.1% of that mass is carbon. And I can do the same thing for my other elements. Hydrogen, you may notice again, makes up a very small percentage of the mass. And that's because, again, hydrogen is a very lightweight element, at least by comparison. And so I can come up with my percent compositions for these other pups. Neat stuff. Well, why don't you pause the video and try coming up with a percent composition for insulin? That bad boy. Wow, that's a big molecule. But you can do it. Give it a shot. Cool. Well, you pause the video. Let's talk about it together. First thing we're going to do is get that total molar mass. And, I'm going to just record my work because it turns out I'm going to need to know the mass of each element as it makes up this thing. So I'll take my mass of carbon, my molar mass, and multiply that by how many carbon atoms there are. Bam! Got a number. I'm going to go through and do this for each one of my elements. The hydrogen, the nitrogen. Wait, there's 65 nitrogens. The oxygen, there are 79 oxygen atoms in this. And also for the sulfur. Not a lot of sulfur, only 6 atoms. But they're important. Okay, well, I add all those up to get my total molar mass. And now just for each element, I've already done this step where I get the mass that each element adds to the compound. I'm just going to divide the mass of each element by the total molar mass and multiply that ish by 100. So I'll take my total mass of all the carbons divided by the total mass of the whole molecule, multiply by 100, bam. And I can do this for each one of my elements. I'm just going to record those back up there just to keep things nice and neat. So 21.6% of the mass is oxygen, and I'd call that 3.3 if I were rounding. Percent of the mass is sulfur. So this problem isn't actually that spicy. It's fairly following the same steps. The only thing that looks spicy is just there's a lot of each element. But that doesn't really make any things harder. It just changes the numbers you're plugging into a calculator machine. All right, well, let's talk about empirical formula versus molecular formulas. Okay. Molecular formula, well, that's what tells us what's really happening in a molecule. It describes the full formula of a molecule and accounts for every single atom. So for instance, I got my example molecule here. This is cyclohexane. And in cyclohexane, I can count there are 6 different carbons and there are 12 hydrogens total. My formula is C6H12. It accounts for every single atom in the formula. But an empirical formula is different. An empirical formula is going to have a simplified formula, and it's typically going to be obtained from the percent composition. The ratio of elements is going to be made as small as possible in my empirical formula. So 6 to 12 is a ratio that I could simplify. And this is going to result in numbers that are smaller, having smaller subscripts. So for this same cyclohexane, my empirical formula is going to be CH2, 1 carbon, 2 hydrogens. And I get that by reducing my subscripts in the actual molecular formula and dividing them by 6. So 6 divided by 6 is 1, 12 divided by 6 is 2, and that gives me my CH2. You might say, why would you ever use an empirical formula? But sometimes calculations will just give you an empirical formula. You don't always end up with the molecular formula as a result of calculations. Neat. Well, let's talk about how we can calculate the empirical formula using percent mass. Here is an example. We have an unknown compound, which is 24.02% carbon by mass and 75.98% fluorine by mass. What's the empirical formula? Well, we're going to follow 4 simple steps here. First is we're going to change those percents into grams. And you can skip the step if you're already given masses to start with. I'm going to take my 24.02 grams of carbon, or percent carbon, and just say that's grams. My percent becomes a grams. And for my 75.98% fluorine, I'm going to say that's 75.98 grams of fluorine. Not too spicy. Actually, that step's really easy. Second step is I'm going to convert these masses to moles, and I'm going to use the atomic weights, or molar masses, from the periodic table. That's not too spicy either. I take my 2 numbers, I'm going to X-line that action, and use my molar masses. And yeah, I can quickly and easily convert to moles. Really, really not spicy at all. Third step, I'm going to look at these numbers that I get after in step 2, and I'm going to divide each of the number of moles by the smallest number of moles. What this is going to do is give me a ratio to figure out if there's 1 mole of this, how many moles of this other element there are. And so I always want to use the smallest number of moles to keep my numbers nice and happy. So 2 moles of carbon is the smallest number I got out of step 2. So I'm going to divide all the numbers that I got out of step 2 by this. 2 carbons divided by 2 seems silly, but that gives us the ratio for carbon. 4 fluorines divided by 2 gives me 2 fluorines. And so now these numbers are my empirical formula, provided that they're all whole numbers. I want to have all whole numbers, which I do here, so I don't need to do my last step. If one of these numbers wasn't a whole number, I would have to multiply both of them by the same integer value to get whole numbers. We'll look at an example of that next. My empirical formula here, nice and easy, is 1 carbon, 2 fluorines, CF2. Sweet. Well, why don't you, oh, right, I forgot. Here's the silly thing that my teacher in high school said that is still drilled into my brain years later. The way that they talked about doing this is we went from percent to mass, step 1. We went from mass to mole, step 2. We divided by small, step 3. And we multiplied till whole, which that part's silly. But then I was like, you could actually make a really crappy rap song out of this. So if you want to do that, be my guest. But why don't we practice one more problem? Why don't you give this one a shoot, and we'll go through it together. Sweet. You pause the video and try it out. Let's do it together. Well, step 1 is percent to mass. I'm just going to take my percentages and turn those into grams. All right, step 2 is mass to mole. I'm going to take my masses and convert those to moles using the molar mass of each element. So I'll use my molar mass of my carbon, I'll use the molar mass of my hydrogen, and I'll use the molar mass of my oxygen to come up with the number of moles for each one of these babies. All right, well then step 3 is divide by small. So which of these is smallest? Oh, it's my 2.74 moles of oxygen. But I'll divide each of these values by 2.74. So take my carbon, divide that by 2.74, it gives me 1.5 moles of carbon. That's a nice ratio number. I can do the same thing with my hydrogen, which comes out to a pretty nice 2.5. And then for oxygen, when I divide 2.74 by 2.74, yeah, it comes out to 1. Okay, well, last step, multiply till whole. These are not whole numbers. So what I'm going to do is I'm going to take all of these numbers, and I'm going to multiply all of them by the same value. If you're not sure what to multiply them by, just by looking at it, you might want to start by multiplying everything by 2, then multiply everything by 3, then multiply everything by 4, and just so on until you have nice whole numbers. Well, in this case, if I multiply everything by 2, shazam, we get some nice whole numbers, and I get an empirical formula of C3H5O2. Sweet. Well, that is the end of this video. I hope you understand a little bit about how mass composition works, or percent composition by mass, and also how to use that to calculate an empirical formula. Anywho, ta-ta, have a great rest of your life. And close. Because you do not have an editor.